Here we have a capacitor. It's a 0.6 microfarad capacitor, and we have a voltage across it and a current through it. And in this case, we're being told what the current is through that capacitor, and we want to find out what the voltage is. Well, if we want to go from current to voltage, we need a starting point. If the current is switched off for t less than 0, you can usually assume that the whole thing is not in operation, but it's good for us to be told specifically the voltage is 0 as long as that current hasn't been flowing, and then once the rest of the circuit supplying this capacitor switches on, then the voltage is going to change, and that's what we're looking for. So we're given the current here, we want to find the voltage, and there's an equation for that. So we start out with our equation using the current to find the voltage. In this case, the capacitance C is a fixed value. That's something that depends on the fundamentals of the capacitor, and that's given. This value right here is 0.6 microfarads. Also, we need a starting point, we need a time, and we need to know the voltage at that time. In this case, we're told that when t equals 0, we know what the voltage is at that point in time, and this is 0 as well, so we can plug in those values. If we are integrating from 0 onwards to some later arbitrary time t, well, if we are integrating starting at 0 and going later in time, we know what the current is. We have a function for that. And so we need to rewrite this equation, not having a general capacitor current function here, but plugging in our specific function, but leaving it as a function of this dummy variable, the scripted t. Now that we've plugged everything as a specific function, we can integrate a specific function. Here, the integral of cosine is going to give us a sine, and be careful to use the chain rule. So integrating cosine, I got a sine. I get a factor of 1 over 50,000 coming out from the chain rule. Now I've got three numbers here. I can combine these three into one single value, and then I need to evaluate the endpoints. This is my integral, but I need to evaluate those endpoints. So when I plug in my values, I get 50,000 times 0. That whole thing is 0. And then if I have sine of 0 is always going to be 0. So that whole term goes away. My capacitor voltage in this case is going to be 100 sine of 50,000 t. I was using farads. I accounted for the microfarads there. I was using amps, and so my voltage here should be in volts. Also recall that this is for t greater than or equal to 0. Our voltage was 0 for t less than 0. Next, we're asked to find the maximum power delivered to the capacitor at one instant of time. So what we need to do is figure out the power delivered to the capacitor in general, and then we can figure out how to maximize that. We know that nothing is going on for t less than 0. There was no current, there's no voltage, so the power before time t equals 0 is 0, and that's not giving us anything interesting. So we're going to assume that we are at t greater than 0. The power is voltage times current. We know the voltage, we know the current, and so we can plug those in. I have my voltage and my current, and I'm going to multiply together my constants and rearrange it to simplify a little bit. Now, we're always looking to simplify. Any sort of math that we're going to do later will be a lot easier if we can simplify the function now. Notice that we've got sine of some argument, 50,000 t, cosine of the same argument. And there's a double angle formula that tells us that sine of 2 theta is equal to 2 sine of theta cosine theta, or we can divide that 2 over to the other side if we wish. And so what that tells us is if we have a sine and a cosine multiplied together with the same argument, we can replace that with a single sine of twice that much in the argument. So if this is sine of 50,000 t and cosine of 50,000 t, twice that much would be 100,000 t, and we need a factor of 1/2. So that would give us the following. The 300 times that factor of 1/2 would give us 150, and then instead of having 50,000 t and 50,000 t, we'd have 100,000 t there. We were using our voltage in volts, our current in amps, so if this is power, the power is going to be in watts, and we need to remind ourselves that this is only true for t greater than or equal to 0. Now, if we want to find this is the power at any value of t at any time, but what we're being asked is what is the maximum power. Now, typically, if we want to find the maximum power, we have to maximize a function, which would involve taking the derivative and setting it equal to 0 and figuring out what the maximum power is. But in this case, we can use math tricks. We can see that we have an amplitude here, and then we have a sinusoidal function. This function is going to oscillate between -1 and 1. And so this function is going to be greatest when the sign is greatest, which is when sign equals 1. And when this equals 1 times 150, our maximum power is going to be 150 times 1, which is just 150 watts. The last part of this problem, we're asked to find the maximum energy stored in the capacitor at any instant in time. We know the current, we know the voltage, and we know the power. We said that the power is the time rate of change of the energy in the capacitor, and so we saw how we could integrate the power to find the energy stored in the capacitor. That said, we would have to try to integrate this function, and then we'd have to maximize the energy, and that would be very complicated. If we're looking for the maximum energy, we've already done the work. We've already put in the effort to find an equation for the energy stored in the capacitor, and it's this equation right here. So we already know the capacitance of the capacitor, that's a fixed value. We already found the voltage across the capacitor, so if we already did that effort, we can just plug it in here. There's no more calculus that we have to do, and it'll just be a simpler way of coming to that same energy. And then once we have the energy, we can figure out how to maximize it. So I've plugged in the value of the capacitance, I've plugged in the expression for the voltage. I went ahead and squared this function. If I have this times that squared, it's the first one squared times the second one squared. I took all of these values here, and I simplified them, and I got 3 times 10 to the negative 3, and then I've got my sign term here. And I used capacitance in farads. I accounted for the micro. I have my voltage in volts. And so if I'm looking at energy here, this should be my energy in joules. And so we want to find the maximum value of the energy. Well, we have to notice here that we still have a sinusoidal term. We have some amplitude, and then this here is a sinusoid. Because it's a sine squared, that means that it's going to be oscillating between 0 and 1 in this case. Instead of going to -1, because when sine is negative, the square makes it positive anyway. And so if we want to find the maximum energy, well, the maximum energy is going to be where this function is maximum, and this function is maximum when it equals 1. And so we're going to have 1 times our 3 times 10 to the negative 3 joules is going to be the maximum energy. Three times 10 to the negative 3 times 1 joules, or 3 millijoules if we use a unit prefix there.